Okay, so in the last class, we got some ideas about like the different kinds of forces. Like hydrogen bonding was one of the major ones that we were discussing. Did we leave some unanswered questions in the last class? That I always forget. So I was going through some of my class notes and I thought that the nitrogen, oxygen, that question of the ionization enthalpy was left unanswered. Did everyone figure it out why the ionization enthalpy of nitrogen was more than that of oxygen when the trend says that oxygen's ionization enthalpy should have been greater than nitrogen?
Oh, you're going way back.
Yeah. So let me rewrite this question here. So ionization enthalpy. The general trend should be oxygen greater than nitrogen, because left to right it increases. So this should be it. But in actuality, this is the one. This is not. This is the correct trend for ionization enthalpy. Did anyone not get the time to look at this? Should we discuss this just for a brief moment? It's important. Who has the answer to it, or who wants to think about it?
But it's something with its filled orbitals.
Correct? Yes, correct.
Filled and half filled.
Correct. Go on with it. Go on with that thought.
If I remember correctly.
Just write the electronic configuration and it'll be very clear.
Yeah, so nitrogen 1s2, 2s2, 2p3.
2p3.
Yeah, or 2p3 and then oxygen is 2p4.
Yep. This chalk is actually good. So our job is to remove an electron. And just think about it. Which one would be an easier removal? The nitrogen or the oxygen? Kelsey? Why? You're right. It doesn't have an extra. Yeah, so it is easier to remove this. And why? What is the reason behind it? You're right. It's easier to remove this. I mean, so it's if it is just has more, then how about this? How about this versus this? Whatever this is, this has more. So between this and this, the more thing is not going to cut it. I mean, that's a bad example actually. Okay, let me see if I can find out an example to trick you where more doesn't cut it. This is, oh, so you're saying since this is more, this is going to be easier or difficult? So if more is easier, then this should be easier, right? But this should be easier than this, but it's not. More is not always, actually, more makes it harder because the nuclear charge increases. In this case, yes. Someone, I think you also said something in that regard, yeah, but.
Because half filled is more stable than partially filled.
Yeah, were you getting at this? Yeah, right. It's so this is trying to get half filled, this is already half filled. So if I try to remove this electron, this gets to half filled, it will easily remove that electron. But this will try to hold on to its electrons because it is half filled, and it will not try to release that. So this is the ionization enthalpy. The trend is opposite, and now someone might say, chemistry has exceptions. This is not an exception. If we understand the underlying rules, this actually makes sense. It's not an exception. Exceptions are to rules that like human beings made. I mean, nature doesn't have to conform to human man-made or person-made rules. So Okay. Did we leave anything from last class to discuss? I know that we were at H2O and H2S, and we discussed about why H2O was liquid and H2S was gas, when higher molecular weight means more boiling point. Courtney, you have the sheet that I gave from the Libre text. I think, can you give me a name to that rule? Like what force defines that? Like higher molecular weight means higher boiling point. So you will so if you go ahead. Go ahead. Yes, on this part. So this is the part that is getting explained. Yeah. So if you just tell me which rule is getting dealt. So you see that top part? Yeah. So that is what is explaining. So it's like higher surface area means more boiling point. So what's that interaction? What are they calling this? The people who actually know their things what they're saying, not like me.
Is it the London dispersion force?
So London dispersive forces says that higher molecular weight will bring in more boiling point. But H2O, although it's less molecular weight, still has more boiling point, and that's why it is a liquid, because of hydrogen bonding. Life sustains because of hydrogen bonding. DNA, so you have like the DNA, the double helical structure, so you have like four, I think Venus will be able to like correct me if I'm wrong. So ATCG, so A and T combines and C and C, right. So there is adenine, what is T? Thymine, guanine, and cytosine, right? So they also have hydrogen bonds, right? So hydrogen bond, so you see that double helical structure that goes in. So there are hydrogen bonds that are maintaining that helical structure. So that is, the helical structure is being maintained due to hydrogen bonding. So if hydrogen bonding did not exist, the DNA structure would fall, and so shall we, right? So it's really important. So hydrogen bonding is not just for water, although water is very important. So it will play its part in like different kinds of really, really important things. And I think curling of hair, so is also due to hydrogen bonds. Because like when I wash my hair, so I have like a little bit curly. When you wash your hair, it becomes flat, or when you heat it, it becomes flat. So basically when you do that, your hydrogen bonds between, and so your hair is also keratin, which is also a protein. So there are also, I think, I might have read it on somewhere which probably is false, but I think like you guys can check, the curling of hair is also probably because of hydrogen bonds. And that breaks when it's at higher temperature, and then it again curls because at lower temperature, then again the bonds are starting to form. So hydrogen bonds are like important, okay? Now I was talking about a concept called hybridization. It's a really important concept in general chemistry, and it will become really important in organic geochemistry, organic molecules. This was not a part of the original like the plan, but since we are not even following anything about that original plan, I thought that I'll give you some idea about organic geochemistry, just get some more, get another refresher today. So before doing that organic geochemistry part, let's look into an idea about hybridization. How many of you have heard about this term hybridization, like sp3 hybridization, sp2 hybridization, all this? Just heard. Okay. Have you? Okay. Okay. So hybridization was a really smart way. So this is what happens. In nature, strange things are happening, and we as mere mortals, we are trying to find out the rules by which we can explain the things that are going on in nature. So we came up with this idea about hybridization. So you cannot explain everything by normal bonding. There are many things that you cannot. There's another thing, really important question, is the things about extended octets. NCl5 doesn't exist. NCl3 does, because nitrogen needs 3 more electrons to satisfy its octet. So it has 5, it bonded with 3, so now the octet is met. There's no reason that NCl5 or NCl4, whatever, should exist. But PCl3 is the same, so nitrogen and phosphorus are in the same 15th group, nicogens. So PCl3, fine, there's no problem. But there is a PCl5 that exists. This is called extended octet. Same goes for SF6. SF6 exists. No reason that it should. Like no reason that we came across in the class that it should. But it does exist, SF6. Another case of extended octet. Why do you think these things are happening? Another important part is PCl5 exists, PCl3, pH3 exists, but pH5 does not. So extended octet exists here, but not here. So this is not happening. Can you take a guess, like just look into a simple example? NCl3, PCl3 is fine, but PCl5 exists. Why do you think the PCl phosphorus went to form more bonds than it should? Or how is this possible that phosphorus went ahead and made 5 bonds? How is it possible? But NCl5 is not doing it. What's the difference between N and P that you're getting an extended octet here but not here? I'm not an expert on these things, but I'll give you the knowledge that I have. What's the difference between N and P? Always go back to electronic configuration, always. Just think, what is there in P that is not there in N?
Isn't it an extra shell?
It doesn't have an extra shell. So what's the configuration of phosphorus? Okay, let me not put you guys through this pain. I mean, okay. So because of that because of the presence, because of the availability of those extra shells, it can actually take the electrons from C and put in those shells. So just think of that in that terms. N does not have someone does not have extra rooms to house people. It's like that. Phosphorus has extra rooms to keep the electrons that are coming from chlorine. That's the very rudimentary way of things. It is not as simple as that. Even I don't understand it, or I don't remember it clearly, how the different things are happening. I have to go back and see. But please bear in mind that these things do exist. Like, not everything wants to follow that octet rule. Another thing is BF3, boron trifluoride. It's another case in which you don't have fulfilled orbitals. It's like 6, but it still exists. In this case, this forms a dimer with another BH3 and forms a B2H6 molecule. There comes the term of a shared pairing, a really weird kind of sharing. We call it 3 center 2 electron or something like that. A 2 center 3 electron bond or banana bond. I think you'll have some information on your sheet. But I just want to impress upon you, not everything will have this this completed octet. Okay, now let's move on to hybridization. Because these things, stuff like these existed and many more, we came up with this idea of, and I'm just saying it's an idea, we do not know whether that exists or not. It's just an idea that explains many observations. That when you have these different orbitals will come together and form hybridized orbitals. Okay, so this is like an entire concept that cannot be dealt in like one small class. What I'm going to do is not trying to understand, not trying to give you everything that goes behind like hybridization, but I give you the tool that will be able to use hybridization to predict structures of molecules. That's what we'll do. We'll not try to understand why hybridization occurs, the mechanics of it. We'll just try to use hybridization so that we can predict structures of things. Like if methane has a tetrahedral structure while CO2 has a linear, H2O has a bent, how did that happen? So we'll just try to do that in this class. Okay. Now, when you are so the things to keep in mind is like different orbitals will come together and they will form hybridized orbitals. So like many orbitals will come, not many is not the right word, multiple orbitals will come and they will form multiple hybridized orbitals. The hybridized orbitals will be somewhat of like a mixture of these two things. So the hybridized orbitals will take in the properties of these individual orbitals. Also, the number of orbitals in here, the number of orbitals taking part in the hybridization process will be the same number of, like if 2 orbitals are coming in, the number of hybridized orbitals produced will be 2. 3, then 3, 5, then 5. Whatever comes in is an equal number is being produced here. And this will get the, like a property of all these different components. Okay. Now, let's try and see from an example. So if an S and a p orbital comes together, they will form an sp hybridized orbital. So one orbital and one, so you form one sp, something like that. So number of like these orbitals will match the number of hybridized. So we got one s and one p, 2 in total. So we got 2 sps. That's the idea. You have s and 2 p's, so we get an sp2. We get an s and 3 p's. So there were only 3 available. So all these 3s are getting together, we are forming. So if how many orbitals are getting involved in here? Number of orbitals. In here it was 2, here 3, because we are getting 2 p orbitals getting involved. Here we get 4. So 3 from the p and 1 from the s. So there were like 3 orbitals available for p anyway. So like you had a px, a py, and a pz. So in here only p was getting involved. Here only one of them were getting involved. 2 were getting involved. All 3s are. What's the next do you think will happen? sp4? And yeah, why not sp4 or sp6? I gave the answer like it's not going to happen, but why not? Because you don't have 4 p orbitals, you just have 3. Right, so what's the next thing that you can imagine? Yeah. So you get an sp3d. It's as simple as that. So 5 and 5 sp3 orbitals, things like that. Okay? Now, let's look into a concept called interactions, in which there are 3 types of interactions that can happen between pairs of electrons. Now, electrons can be a bonded pair of electrons, as we saw earlier. In here, we saw for the case of H2O, there was this lone pair of electrons that were here, right? And in case of NH3, ammonia, we also saw the lone pair. So there are 2 types of electrons. One is a bond pair of electrons, and another is a lone pair of electrons. There could be interactions between them. There could be a bond pair interaction. There could be a bond pair. There could be a bond pair lone pair interaction, and there could be a lone pair interaction. What do you think is the most energetic of these interactions? Or if there is a lone pair interacting with another lone pair versus a bond pair interacting with another bond pair, which of them do you think will be more, what do you say, energetic or more forceful or more intense?